Welcome to our third example of Bernoulli. Please make sure you watch the previous two episodes where we have two other examples, and in particular in example 1 I went over what is Bernoulli. So Bernoulli in general can be written this way, where P and Q are function of x or function of t. In this case it's a function of t. And you can look at here, we're thinking y as a function of t here. So t play the role of x. And the substitution will always be v equal to y to the power 1 minus n, whatever that n is. So the first step, we need to write it down in the correct format. So I have to make the coefficient of dy dt 1. So you have to multiply both sides by t to the power negative 2 to make it a 1, right? So let's do that. But of course you have to do distribute property, right? So let's do that. So I get, so this is going to be just dy dt plus t to the power negative 2 y square equal to, and when I multiply this out I get t to the power negative 1 y, because remember there's an invisible 1, and when you add you get negative 1. Let's continue. It's not in the correct format because the y to the power n must be on the right. So here the y to the power n, which is y square, so that term must be in the right. So I have to switch, I have to just move this term around. So let's do that. Once you do it, it's in the right format. So I get dy dt. So I'm moving t to the negative 1 y to the left, so that becomes negative t to the negative 1 y. And then the other one I'm moving in the right, so I have to switch the sign, right? So I get negative t to the negative 2 y square. So this is in the correct format, and you can see that this is the p. So p is negative t to the power negative 1, and this is the q. But most importantly, the n is 2. So let's do the substitution. So the substitution is v equal to y to the power 1 minus n. But here the n is 2. So I replace n by 2. And I get y to the power negative 1, or 1 over y. So we take the derivative of both sides with respect to t. Remember, t is the independent variable. So I'm looking at this. So I bring down the negative 1 in the front. Y to the power, I subtract 1 from the exponent, right? So that will be negative y to the power negative 2 times, oh, and then of course you have to times it by dy dt. That's the chain rule. That's very important. Remember, you're thinking y as a function of x. So don't forget, at the end you multiply by dy dt. So let's solve for dy dt. So I have to get rid of this. So you can multiply both sides by negative y square. So let's copy this. And of course, when I multiply them, I get 1. And negative times negative is positive. And y to the power negative 2 and y square is y to the power 0, which is 1. So all I have is dy dt. So we solve for dy dt. At this point, you substitute your dy dt in place of dy dt. So that's what we're going to do now. So let's do this. And I will do it here. So let's do the substitution. So in place of dy dt, I write negative y square dv dt, and then copy everything else. Not going to change anything, just copy everything else. So here you can see I have three variables, v, y, and t. So we have to get rid of y. To do that, at this point, the step is you need to make the coefficient of dv dt 1. So I have to make this coefficient of dv dt 1. So let's do that. And how I do it. So here you need to multiply both sides by negative y to the power negative 2. Right? So I have to make the coefficient 1. So the reciprocal of negative y square is negative y to the power negative 2. So let's do that. I'm multiplying both sides by negative y to the power negative 2. So of course I'm going to end up with dv dt, because negative y to the power negative 2 and negative y square is 1. Negative times negative is positive, and y to the power negative 2 times y square is y to the power 0, which is 1. And here I'm just going to multiply out. So let's do that. So I'm going to have negative times negative is positive. So just to show you here, this negative times negative, that's positive. Copy the t to the power negative 1, and then y to the power negative 2 times y. So that's y to the power negative 1 equal to, here copy negative, actually negative times negative, that's positive. So I'm going to just write, so that's positive. So I have t to the power negative 2, and then of course y square, and y to the power negative 2 is 1, right? So all I have is just t to the negative 2. It's very simple, looks very simple, but it still have v, y, and t. But remember the relation between v and y. So let's go back. What is the relation here? Right there. So v is equal to y to the power negative 1, right? So v is y to the power negative 1. So this y to the power negative 1, that's your v. So that is the substitution we make, right? So let's replace y to the negative 1 by v. Now there is no y, and it is linear in v. So v play the role of y. V is the unknown function, and this differential equation is linear differential equation, which we already know how to solve. So this is the p and this is the q. Again, do not confuse this p and q with the previous p and q. So this p and q is for the linear. So let's use the formula. The integrating factor is e to the power integral of p dt. In this case, t is the variable. So I get e to the power integral of t to the negative 1. But t to the negative 1 is 1 over t. And the integral of 1 over t is ln of t, which is just t. E and ln cancel each other. They are inverse function. And here we can assume t is bigger than 0. So the v is going to be equal to integral of u q over u. So let's substitute. My u is t, and the q is t to the power negative 2. So let's do that. So it's t times t to the power negative 2 dt over t. So let's find the answer. So this is when I multiply t and t to the power negative 2, that's just t to the power negative 1. Remember, there's the invisible 1, t to the power 1. So when I add, I get negative 1. And of course, the integral of t to the negative 1, which is t to the negative 1 is 1 over t. So the integral of 1 over t is ln t. So I get ln t. I'm going to drop the absolute value because we're assuming t is bigger than 0. So it's ln t plus c over t. Here you have to add plus c because you are finding the solution. For the integrating factor, here no need to add any c. Your c is 0. So let's continue here. So I can replace v by, remember, v is y to the power negative 1, right? If you look at v is y to the power negative 1. So let's replace v by y to the power negative 1. So y to the power negative 1 is actually just 1 over y. So let me just write 1 over y equal to this. So what is your, I can actually flip around and find my y. So if I just flip around, so I get y equal to t over ln of t plus c. So I flip both sides. Because this will nicely give you an explicit format. So that's very good because we actually find explicit format. So this is a explicit solution. Very nice. I really want to draw it. Let's actually see if we can draw it. Let's go to the GeoGebra. So remember, it's t over ln of t plus c. So let's see how the graph looks like. So let's look at the GeoGebra. So you start with c, enter. That gives you the slider for c. And I'm just going to enter the function. Instead of t, I'm going to use x because GeoGebra understands x better than t. So let me just use x instead of t. So remember, the solution is, let's check, it's t over ln of t plus c. I will enter x over ln of x plus c. It doesn't matter. The graph will be the same. So let's do that. X over ln of x plus c. Of course, my x is bigger than 0, right? So only looking at the right hand side here. And this is the graph when c is 1. And of course, you can play around, right? If you zoom out, you can see the bigger picture. If you replace x by the absolute value of x, then you are going to get the right hand side. Excellent. Always remember, you can do it. Thank you.